Hi, I'm Reyne from the University of Sydney, and I'll be talking through sample problem O. Now, as I've done with other examples, I'm going to talk through the three tests at the beginning first, just because it helps to narrow down our options when we start to consider some of the other data. So first of all, for an unsaturation test, we can see we have a negative response. There are no double or triple bonds present. For our oxidation tests, we can see another negative response, meaning that there's nothing that can be oxidized present. And then finally, for the carboxylic acid test, we can see that there are no bubbles. So another negative response, no carboxylic acid presence. I also like to skip IR and mass spec and come back to these later. They can be a little bit harder to interpret just at face value, whereas the carbon and the proton data, that tends to tell us a little bit more about the backbone of the structure, and therefore we can confirm things with mass spec and IR. Now, carbon NMR, I'm going to just label these arbitrarily peak 1, peak 2, and we can see here quite a big height difference between these, potentially 2 to 3 times larger. And while it's hard to quantitatively use this, it does give us an indication that there are likely more carbons that fit peak 2 than there are peak 1. So we'll keep that in mind as we go through, and the proton should hopefully give us a bit more information about that. The other thing to note is that peak 2 is kind of sitting in the alkyl carbon sort of region at about 30 ppm. Peak 1, however, is de-shielded. It's been shifted downwards, so it's down at about 70 ppm. Now, that's not a crazy amount of de-shielding like we'd expect to see in, say, a ketone, so a carbon double bond oxygen, or a carboxylic acid, even though we've already ruled that out. But some other things could potentially de-shield that amount. So something like an alcohol, something like even maybe an amine. I can't remember the exact regions of where that fits, but we do have evidence here that there is something that is causing that de-shielding effect. If we move down into our proton, we see some further evidence of this. So we can see a very small peak, and you'll note here that it's kind of magnified that peak. So it's this whole line thing here is just magnifying that region of about 4.5. So let's call this tiny peak A. And then we have a second peak down near about 1 ppm, which we'll call peak B. And if we come down to this proton peak data table, we can see a bit more about those peaks and what they are. They're both singlets, which tells us that each of those proton environments have no protons in the environments around them. And the ratio of these are quite different. So we can see that the peak at about 1.26 has a ratio of 9, which would suggest that there are 9 protons there. And then the peak at about 4.49 is has a ratio of 1, which tells us that there's only one proton there. Now, what's coming to mind for me here is that if there's only one proton, then it's potentially an alcohol present. We've already seen that there's a de-shielding effect. There's only one proton there. And since there are 9 protons in the other environment, and we know we can't have a carbon with 9 protons on it, this is maybe suggesting to me that there are maybe 3 terminal CH3s coming off a carbon with an alcohol. Now, first thoughts, we have to, of course, confirm this. And this is where we come back up to our mass spec and to our IR. So the first thing I might do before I do mass spec is actually go to the IR, because if it is an alcohol, there's a really obvious signal we expect to see. So first of all, we can rule out this peak here, which we know is our C to H stretch, which you tend to see in most of these. We've got another peak here at about 1450, which is our C to H bend. We can disregard the fingerprint region. It's too messy for us to really deal with. But then we have this broad peak up at about 3500. And that should immediately trigger your brain to think about, do I have an alcohol present? The broadness of that peak comes from the fact that if you have something that can undergo hydrogen bonding, there are tiny variations of what they can do in terms of bends and stretches. So rather than a nice sharp peak, we actually see a broad peak indicative of the fact that there are those differences. So this tells me it's further evidence that we likely have an oxygen. So I'm going to assume that there is an oxygen present, and we'll come back to that. Now, for our mass spec, we've got a molecular ion peak of 74. For some reason, this mass spec seems to be cut off for some reason. We don't actually have the peak for itself at 74, but we've been told that it's 74, so we'll go off of that number. We come down to here, we can see that we have 10 protons according to this. So we've got 10 protons, which would equal 10. We're assuming that there is a 1 oxygen present, which would be 16. And that brings us to 26. And we haven't dealt with the carbons yet because we have this difference in height between the two. Now, we could assume that let's just make an assumption. Let's say that there is 1 carbon at peak 1 and that there are 2 carbons at peak 2. So if we said there was 3 carbons, that would be 36. 36 plus 26 is going to give us 62. And that's short. And in fact, it's short by exactly 12. So at this point I go, well, 3 mustn't be right. The peak is quite large. Let's try instead 4 carbons. So we're saying that there are 3 carbons at that peak 2, 1 carbon at that peak 1. That would instead give us 48. And the combination of all those together gives us 74, which adds up with our mass spec. So we've confirmed the number of carbons and hydrogens. We know that there's an alcohol present. So we come back to that idea with the type of proton peaks that we see, these singlets, and the fact that there are 9 protons for peak B. And that to me suggests that we actually do have this kind of structure where we have 3 terminal CH3s and they're all equivalent to one another. It's kind of hard to draw, but if you think about this 3-dimensionally, if you place or orient your OH straight up, these 3 CH3s are going to be equally dispersed pointing downwards. So if you imagine a kind of a pole going through the OH and through the center of the molecule, each of those CH3s are equivalent to one another in terms of their proton environment and the amount of de-shielding that they feel. So therefore, that's why we have the 1 peak, and it's a singlet. Because the central carbon there, which I haven't talked about yet, that central carbon, which would have been peak 1 up in our carbon NMR, and in fact, maybe I'll draw those in just for confirmation. So that would be peak 1, and these would all be peak 2. And then if we think about drawing in our proton NMRs, that would be B, B, and B for the 9 protons. And then that proton on the alcohol itself would be A. The last step to do this is then to name this. And this one's a little bit trickier than some of the other examples I've looked at so far. But here we just need to go with what's our longest chain. Our longest chain is going to be prop, so 3. So we can say that we've got propane to ol to recognize that there's an alcohol. And we need to also say that there is actually a methyl at the 2 position. So we have 2-methyl propane 2-ol. And that's it. Thanks.